So let's go ahead and delve into metamorphic rocks. First of all, before we get into your notes, let's understand a little bit about how these are formed. This picture shows a really, really deep mine. And as you can imagine, as we've been talking about these layers of sedimentary rock building up on top of one another, you can imagine that the layers of rock that we have here on the Earth's crust go down pretty deep. In fact, on the continents, we have anywhere between 20 to 25 miles of rock layers piled on top of one another. So even the deepest mines that we can dig don't go all the way down to the bottom of our crust. Now, you might remember when we studied plate tectonics that we talked about the fact that along these convergent plate boundaries, we have actual crust being destroyed. So rocks that are along these tectonic plate boundaries, when they converge and subduct, those rocks can actually melt back into magma. So if they get shoved underneath the crust down into the mantle, they will get hot enough to melt. But what happens to the rocks that don't go quite deep enough to actually get into the magma? So if we look at our layer of rock columns down here all the way at the bottom of the crust, these rock layers are right up against the magma, and so they're actually the ones that are melting down into magma. But what about a rock that's, say, about here in our column of rock layers? In other words, it's not all the way down into the mantle, so it's not actually going to melt, but it is going to experience some heat. So we're looking at things that are about right here on the Earth's crust. That is where we're going to find our metamorphic rocks. And it's a lot like cookies. If you take a look at this, we have our cookies that are raw dough, and then we put them in the oven and we went ahead and bake them. And you'll notice that the raw dough and the baked cookies are made out of the same stuff. So you can still recognize the little pieces of chocolate chips that were in it to begin with. They're still here. The color is about the same. And the taste is pretty similar. Not that you should be eating raw cookie dough, but anyway, the taste is pretty similar. But what is different about them is that when we add that heat to it, even though it's the same materials and the color stays pretty close to the same, the texture changes and the hardness changes and the layers change. That's what happens to our metamorphic rocks. The word morph is a root that literally means to change, M-O-R-P-H. Now I'm in your notes, that first blank. Morph means to change. And so metamorphic rocks have that word morph because that's what's going to happen. They're going to start as a different kind of rock, and then they're going to change. Now, the other two types of rocks we looked at started as something else that wasn't a rock. Igneous rock came from lava or magma, and sedimentary rock came from sediment. But metamorphic rocks are called metamorphic because it literally is starting as a different kind of rock, and then it's going to change into a new rock. And that rock that it's starting with can be igneous. It can be starting with a sedimentary rock, and it actually can even start with another type of metamorphic rock and then change into a new kind of metamorphic rock. So let's understand that process. Before we take a look at the types of metamorphic rocks, let's look at how they're actually formed. And there are three basic understandings that you need to get from this to understand how these metamorphic rocks are formed. First of all, there are rock layers that are happening in those deep, deep down rock layers that are close enough to the magma of the mantle to get baked by its heat. But they're not close enough and they don't get hot enough to melt. So they're not going to be like igneous where it's formed from actual completely melted lava or magma. Instead, it just gets baked. So if you look at this rock layer right here, it's pretty deep down, close enough that the magma that's here in the mantle is baking it, but not enough that it will completely melt. So the first component is heat. The second thing is that these rock layers are so deep down in that they literally have miles and tons of rock layers on top of them. So coming from the top, there is pressure. All the stuff that is above it and on top of it is pressing down on those layers so they get tightly packed together. And so that means that the texture of these rocks is going to change, the hardness of the rocks is going to change, and the layers of it are all going to get compacted together. So since that original rock is going to change in all three of those ways, we're going to classify it as a brand new rock. It's still going to have the same materials in it. You're still going to see the same colors in it. Like you can see the little crystals here in this animation, but it's going to change into a brand new rock because it will look so different. So just to review in your notes and make sure you got all those blanks, I'm going to point out those things in this diagram here that's from your notes. So we have heat that's coming from the magma that's in the mantle, and we're talking about these rock layers that are around that are really deep down, but not close enough to actually melt. So heat is baking them. Meanwhile, all the layers of rock on top of it are creating pressure, and that weight is squeezing these layers of rock together. And then finally, because of that, the texture, the hardness, and the layers of those rocks are going to change. So that's why we're giving it a new name and making it a separate group. So let's go into some of those different types. Go ahead and pull out your rocks number 2, which are labeled granite. And you should have 2 of those because if you remember, granite has different colors to it. It will have that pinkish color if it's got the mineral feldspar in it. If it doesn't, it just looks black and gray. And so you have 2 different samples of it. That originally was magma that cooled and hardened underneath the Earth's crust. And this picture shows what happens to that granite over time. So it's a little animation here. We've got pressure coming from all the weight of the rocks above it, and we've got heat that's slowly baking it from the mantle. And when that happens to our granite rock, that pressure and the heat turn it into these rocks. This type of rock is called, you ready? It's called gneiss. Yes, that's right. It is called gneiss, N-I-C-E. That's how we say it. But it is spelled very weird. And that's because it's actually a German word, not an English word. So it's spelled G-N-E-I-S-S. So granite, when you add heat and pressure to it, turns into this new rock called gneiss. And if you look at our original granites and compare that to the gneiss, you really can see how it changed. It's like that chocolate chip cookie that was raw and then got baked. The colors are the same, the ingredients are the same, but the texture has changed and the layers have changed and the hardness has changed. Now it's gotten even harder. So this type of rock, gneiss, has tight bands of color. And just like granite, it has those beautiful layers, and so it is often used for things like floors and countertops. By the way, if something is nice, don't take it for granted. Yes, let me say that again. If something is nice, don't take it for granted. See, there you go. I did make you smile. Haha. Okay, moving on. Let's look at rock number 6. So this is shale, and depending on your rock samples, you might have any one of these colors. So this is the sedimentary rock shale, which was formed from mud that compacted together and cemented. And it can be any of these colors depending on how much clay it has. When we add heat and pressure from above and heat below, then it changes into this rock over here, which is called slate. So taking a look in your rock samples, find rock number 11 in your samples. That is slate, and you'll notice there's a slight color change here. It becomes a little bit shinier, and the layers that were wider now are more pressed together and compacted. And slate is really known for having those layers, and you actually can separate it kind of easily by those layers. Now, when this rock was shale, it was mud that had hardened, it actually still allowed water to seep through it. Now that it's in the slate form, those minerals are so tightly packed together that it is waterproof. So in poorer countries, they actually use slate as a material for their roofs because it is waterproof and it's pretty readily available, and they can peel it off into layers to make their roofs on top of their houses. And then it also can be used for floors. We even use it as floors around here. Now let's take a look at rock number 8. Pull that one out. That is the sedimentary rock sandstone. And if you remember, it is made out of sand that's been compacted and cemented together. In this animation, you can see the little crystals of sandstone, and we've got pressure from above as well as heat from below that is baking that sandstone. And as it does that, our original sandstone, as it's exposed to pressure and heat, turns into this rock right here. This is rock sample number 13. Rock sample number 13, which is called quartzite. Quartzite, and let me spell it for you. That first letter there is a Q, Q-U-A-R-T, Q-U-A-R-T-Z-I-T-E. And it does actually look like it's got the little word quartz inside of it, which is the main mineral that it's made out of. Depending on your rock sample, the colors may not match up really well between your number 8 and your number 13. So if you look at my pictures here, you might get a better idea of how it works. You can see that we've really got the same colors in it, but now that we've added pressure and heat to it, now those layers have become more distinctive. And instead of it having these larger crystal grains of sand, now it's all tightly packed together. So quartzite is very glassy and it's very, very hard. In fact, it's the type of rock they put underneath railroad tracks to protect those tracks with all the weight of the trains that are going over top of them. The last type of metamorphic rock we're going to look at will start as number 10. So rock number 10 is our limestone. Remember, that's made out of the dead seashells at the bottom of an ocean floor. We'll add pressure from the weight of rocks above it and heat from the mantle as it goes deeper and deeper down into the Earth's crust. And this one has a pretty distinctive color change here. Number 10 limestone, when it adds pressure and heat to it, turns into the metamorphic rock sample number 12, which is marble. Yep, marble, M-A-R-B-L-E. Now, marbles, those little glass spheres that you play with in different games, marbles used to be called marbles because they used to actually really be made out of marble rock. Today, they are made out of glass. So we still call them marbles, but just so you know, they're not actually made out of marble rock. However, you probably have seen some marble rock. It is very sparkly. That limestone changes colors because it crystallizes and turns into this beautiful white color. Occasionally, it'll have specks of other colors in it, like brown or black. And it is used as stone to decorate fireplaces. It can also be used as countertops, and it's used in different types of buildings. So that is all of our different types of metamorphic rocks. And again, each one of those started as a different type of rock. We added heat and pressure and got a brand new kind of rock.